So let's review the Voltaic cell quiz you took today. All right, so given the following electrochemical cell, we have a voltmeter, we've got this salt bridge, which is screaming to me a voltaic cell. I gave you the metals, okay, and I gave you the solutions. So what do we have to do here? What we have to do here is we're going to have to identify all the parts. And I was able to, let you know those things. So down here in the diagram above, label the anode, label the cathode, okay, and of course indicate the concentrations that needed to get a standard net potential. Label electron flow, label all half cells, include the movement ions and salt bridges. Okay, so now that I know what I have to do, let's do that. So the first step with a voltaic cell problem is we have to find our anode and cathode. These are the usually metals that allow for the redox or give the place for the redox to occur. So I've got silver and zinc. I have to know who is better at oxidizing. So I want to go to the net potential table to see who is better at oxidizing. Table of the standard reduction potentials, all written as reduction gaining electrons. And using our hints of voltage, which is a measure of spontaneity, we can do this. So we've got zinc and we've got silver. And so all we're going to do is we're going to scroll down and we're going to find our zinc and our silver. So we see our silver, okay. Silver, its ability to oxidize. See, we're looking at the metals and saying who is a metal that's better at oxidizing, which means we're moving in this direction. This is written in the other direction. So silver's ability to oxidize is actually negative 0.8 volts. And negative voltage means not very spontaneous. It means you have to add 0.8 volts to make it happen. So we need to move further down. And as we move down, we're going to find our zinc at some point. And there it is. And there's our zinc going in the reverse down here. We change the sign, positive 0.76. So clearly the more reactive metal is the zinc. Now, another piece of information to think about is that where is gold? Gold is a non-reactive metal. Non-reactive metal, okay? And it's way up here, and its ability to oxidize is negative 0.15. So as you move down, you find the more reactive metals. But we found clearly with the greater or the most positive, okay, oxidative potential, which is reverse the standard reduction potential, is zinc. Therefore, zinc is my anode. Let's go back to the quiz. So zinc is my anode. And a good mnemonic to remember is anox, red cat. And the anode is the place of oxidation, and the cathode is the place, okay, of reduction. So this is going to be my oxidation half cell. This is going to be my reduction half cell. We're splitting the redox reaction. Okay, so what's going to happen is a piece of zinc is going to oxidize. And so I can actually start writing my half reaction here. So I know that zinc 0, okay, the oxidation, anox, is occurring at the anode. Zinc 0, which is a solid metal, is going to become zinc plus 2. You say, how do I know it's zinc plus 2 and not some other charge of zinc? Well, because zinc only becomes plus 2, all right, and plus 2 electrons. And you may say, again, how do I know that? All right, well, one key here is that in the solution, they said you had zinc nitrate. And you should know that nitrates are -1. And there's 2 of them, so there's -2 overall. So we're dealing with zinc that has a plus 2 charge here. Okay, I should put a plus 2 charge here, so plus 2 here. Another place you could look is your basic reference tables that I've given you for the quiz, okay, to use. So I'm going to go there now. This table called Table E has this charge there. No need to memorize it. However, you can be using it so much it's going to become common habit. So there's nitrates -1. All right. Another place we could look, all right, in terms of ion F, or as I like to call it, table foo-foo. Okay, and there's your nitrate ion. Okay, very soluble, stretching out a -1 over a large area. But to find out if zinc is plus 2, okay, a good place to go is the Regents periodic table. And in this periodic table that I've zoomed in, and here's zinc, okay, the upper right-hand corner tells you what charges they love to become. Okay, so if you look at the alkali metals who are off to the left, okay, we can see, hopefully here, when we move to the left, okay, we can see these alkali metals, they all become +1. This doesn't tell you what charge they are in the periodic table. They're all written as atoms. Atoms are electrically neutral, protons equal electrons, but these are the charges they like to become. These all like to lose one to become like a noble gas. These like to lose two. So where you are in the periodic table does give you a great clue of what the charge is. Now zinc will do that once we learn about s and d orbitals. Okay, if you go to the right on the periodic table, if you were to go to see where the nonmetals are, you have these guys right here who love to, nonmetals, the small atoms, love to get negative. F needs one more electron to become as stable as neon. Oxygen needs to get to what? 2 more electrons. So you can see that these elements all here love to become -2. These elements who are 1 away from gaining electron to fill the shell are -1. Notice nitrogen is 3 away. Carbon is 4 away, right? 1, 2, 3, 4. They need as many electrons as it takes to fill a shell, and the guys over here will lose as many. One other point is this staircase here, okay, is the separation between the small elements that love to attract electrons because coulomically they have a small distance between the electrons and the outermost electrons and the positive protons. They have a small radius. Everything to the left here are metals, and they tend to have a large difference, a distance between the protons and the outermost electrons, and they have a huge radius, and therefore these electrons are felt less by these protons, and they're easier to lose and therefore oxidize. It's Coulomb's law, right? You can't find me a metal that becomes negative. Metals do not, okay, reduce and gain electrons. So they never become negative. So all metals become positive. Non-metals have an ability to become negative. That's important. So let's go back to the quiz. Okay, so let me correct some errors here. Number 1, the charge is +2. Oop, I crossed that. Is +2 overall there. And let me also correct for the fact that I was stuffing this entire half reaction on one side. We have reactants and products. So in any case, we have zinc by itself, zinc 0 solid, becoming zinc +2. We now know where and why zinc becomes +2, and more importantly, we know where to find what ion it likes to become in your reference tables. And of course, to balance the charge, we need 2 electrons. -2 and a +2 is 0. This side is 0. Both sides of a half reaction have to have the same charge. Okay, who gets reduced? Well, electrons get pumped or pushed by the zinc, okay? And they get pushed always to the cathode. Electrons always flow from anode to cathode, and these electrons build up. Okay, already in solution, I have silver nitrate. Well, as we saw in table foo-foo, nitrates are always soluble, which means, yes, you're going to have nitrates. And I need to write all the ions, and I'll do this on this side. I have nitrates on this side because I have these zinc nitrate dissociates into zinc +2, and 2 of these polyatomic ions. These are clusters that stick together that have a charge. This is going to dissociate in water because all nitrates are soluble. They have weak Coulombic attractions. It is going to become an Ag+. It's a metal, so it becomes positive, and a nitrate. Okay, so that's what happens when they dissolve. So I'll have Ag+ already in here. Okay, so what's going to happen is, well, the silver can't reduce. Remember, the cathode is the place of reduction. So the silver is not going to reduce. It's going to be the place of reduction. If silver was going to reduce, it becomes negative. And as I said, metals never become negative. They have no ability to attract electrons. Their ability is about losing, oxidizing. Okay, so who, in essence, does the reducing, or who gets reduced? Silver ions, or the silver ion has an ability to grab these electrons. So what happens is silver plus, okay, Ag plus aqueous, all right, all these ions, metal ions are aqueous, is going to gain an electron. Now, why one electron? Because it's plus 1. And it's going to make silver 0. Okay? And so it's going to gain enough electrons. You say, well, how do I know it makes silver 0? Well, if it's positive, we know it's going to attract negatives, and it's going to stop once the metal reaches 0, which is the elemental state, which is the solid. Which means there's going to be what? Plating going on here. This electrode's getting bigger. This one's getting smaller as we make zinc plus 2. And I didn't draw that here, right? Solid zinc becomes zinc plus 2 and gives off 2 electrons that are pushed toward the cathode. The cathode, in the solution, the silver plus, is going to help pull that charge forward as well and gains enough electrons to become 0. Now, this half reaction isn't balanced because we are losing more electrons than we're gaining. So I can't accept this to be correct. We're losing 2 electrons. Here we're gaining an electron. In this process, okay, we're losing an electron. We can't basically do that. We have to say a law of conservation of mass, and that essentially electrons are neither created nor destroyed, so therefore there has to be an equal amount of electrons produced and accepted. Okay, so how do we do that? Well, if there's 2 electrons here being produced on the product side and 1 being absorbed, we have to balance them. And we do that by the distributive property of math. We're going to multiply a number all the way through the bottom half standard half or the reduction half cell here, so that we have 2 electrons. Okay, I can't just multiply this by 2. I have to multiply everything by 2 because 2 Ag pluses would need 2 electrons to make 2 of these. It's a 1-to-1 ratio. And the reason why I'm multiplying by the number 2 is to get to 2 electrons, or the common factor of 2 and 1 is 2. So I multiply by 2. This becomes a 2, and this becomes a 2. Okay? And now we have the correct half reactions. I can accept that. And now, all right, we can cross off those things that are no longer going to be part of the overall net ion, because if I gain 2 and lose 2, net I don't have any more than I started with, correct? If I give you $2, or if I lose $2 but then I gain $2, there's no net change in money. So we rewrite, okay, everything here, okay, with these coefficients now. 2Ag plus, which is an aqueous, plus a zinc 0, which we should know is a solid, goes to 2Ag0 plus zinc plus 2. And one good check to make sure you did it correctly is the total charge on both sides have to be the same. When you're writing a half reaction, you should always think about the zinc, or the, I should say specifically, the element being oxidized. Okay, the electrons will be on the product side. And in case of reduction, electrons will be on the reactant side, and the charges will drop. This is plus 1 going to 0. Hey, the charges are dropping. Hey, that's what reduction means. The charge drops because you're gaining negative. You gain stuff on the reactant side. Hey, Ag plus 2 electrons makes this. Hey, zinc by itself produces this. Okay, so all these little hints. Electrons should be on opposite sides. If you write them on the same sides, it's wrong. Okay, so it's important you get that. And it's important to write them so that you put the right number of electrons so that both sides of a half reaction have the same charge. Any case, our overall check here is to make sure that we have the same amount of charge. So 2 times plus 1 is plus 2. Plus 0 is we have a total plus 2 on this side. On this side, we have 2 times Ag0, which is 0, and then a zinc plus 2, so this is a plus 2. So we know that we did it correctly. Okay, the next part of this is calculating the E0, or the net potential or the electromotive force. It's got a bunch of different names. The bottom line is, what's the total voltage? Okay, we call it the standard cell potential because we're going to use the standard cell experiment that gave us the reduction potentials in that chart. Okay, well, when we looked at the chart before, we know that the oxidation of zinc was positive 0.76. It was the opposite as written because in the reverse Remember, the standard reduction potential table is written as reduction, so that means that when we want oxidation, we have to flip the sign. It was negative 0.76 when zinc plus 2 gained 2 electrons to make zinc, but talking about the opposite, it's positive 0.76. Okay, now silver, okay, silver gaining 2 electrons here, all right, it actually likes to do that, and that was a positive value as written in the standard reduction potential table. And there we are for zinc going backwards, as we just saw before. And if we go find silver, we don't use the reverse, okay, we use as written, because we found out before, okay, that the better metal was the zinc down here. The worst metal for oxidizing was silver. Why? Because it likes to go to the right. It's got positive volts. The silver plus ion is what? Really good at gaining an electron. That's why we have positive volts. So when you do the net potential, or the electromotive force, okay, which is called E0 of cell, we take the reduction as written, and then we change the sign of the reduction and add them together. Okay, so it's positive 0.8. So positive 0.80 volts as written, because the standard reduction potential is written that way, and we reverse this sign. And then we add them to get the overall. Okay, and I can do this. 6 plus 0 is 6. 8 and 7 is 15. 1.56, okay, volts. All right, and that's all I wanted there. There's nothing more to it. Notice it's a positive value showing it's spontaneous, and guess what? Voltaic cells are spontaneous electrochemical cells. All right, go through our checklist to make sure we labeled the anode and cathode, indicated the boxes. Oh, we didn't do that. Or did we? No, we didn't. Indicate in the boxes the concentrations of these values, okay, of the salts that are dissolved to give us this exact potential. Okay, so in this boxes, I was after the fact that the net potentials, okay, that we get from the standard reduction potential table is based on a little zero here. The zero means standard conditions. And the standard conditions that they used in the experiment to measure the individual half reaction voltages is based on 1 atmosphere of pressure. It's based on 25 degrees Celsius, or 295 Kelvin, and 1 molar solutions. So these are both 1 molar solutions. Okay, and so that's where that comes from. And what else in our checklist do we have? Label electron flow. That's from anode to cathode. I have my arrows clearly showing that flow, okay, right there. And we should know why. It's pretty logical. All right, and then label all the ions in all half cells. We did that, including the movement of ions in the salt bridge with ions. Okay, we didn't do that. Okay, so in the salt bridge, okay, they said we had NaCl. Okay, I'll change color here. NaCl dissociates and is very soluble into sodium ions, the metal ion, and the chloride ion. So we have a chloride ion and we have sodium ions. The question is, where do they move? Okay, now to figure this out, all I have to do is figure out what's happening in each one of these half cells. Well, in the oxidation half cell, we have oxidation. Zinc is becoming zinc plus 2. No, it's a one-way arrow. So as we move to the right, we're building up more zinc plus 2, right? More of the zinc, okay, 0 is becoming zinc plus 2. So it's building up. This beaker is going to get very, very positive. It will get positive without a salt bridge because you're increasing the amount of zinc plus 2. How in the world will electrons who are negative, who will attract a positive, leave a positive beaker, right? They would stay there and want to be attracted. So we need something to combat the increase or neutralize the increase in positive. Well, my friend, that is the chloride ion. The chloride ion, the negative ion, is going to move down, okay, and be attracted to the zinc plus 2, and that will, again, keep that beaker neutral. Obviously, 2 chloride ions would have to move down for every zinc that's made, but it will maintain what we call electrical neutrality, keep the beaker from getting positive, so it doesn't get positive and electrons can flow. What's happening in the reduction half cell? Well, the silver plus ions right here are gaining electrons and becoming silver 0. That means positive ions in the solution, remember these are aqueous, are becoming a solid. What does that mean? Well, that means that you're losing positives. If you lose positives in your solution, this beaker is going to get what? Negative. If it gets negative, how will electrons ever move towards something negative? They repel that. So the positive ion in the salt bridge moves here so that it replaces the positive that's lost. In truth, there's some more things that could happen here. The zinc plus 2 that's released in this process will also move to replace the positive that's lost. Also, on this side, you have a problem of trying to get positive. Well, the nitrate ion could also move, okay, to alleviate the increase of positive. So all those ions move. Now, of course, I made that a heck of a lot more difficult than I had to, okay? But let me just show you those ions. The salt bridge allows the ions to move to maintain electrical neutrality. It doesn't always mean that the metal is going to move left. The positive ion was needed to replace the positive here. The negative ion was here to try to combat the increase in positive. Okay, so that's important. I think I covered that. All right, and then of course the biggest and most important question, all right, was how will the cell potential, the voltage, the E0 be affected if Ki is added to the silver half cell? So if I add Ki should break apart into K plus and I negative. Okay, so that means I'm going to have K plus. Now I know something. K plus is a group 1 ion, always soluble. If I go to table F and remind myself, always soluble. So it's never going to make it precipitate. Now iodine, okay, has an ability. Now you may say, Mr. Grotsky, how do I know I'm going with solubility? Well, is there any K plus in this reaction? In the overall reaction, do you see any K plus? No. Do you see any I negative? No. So there's no common ion effect. None whatsoever. So this must be about solubility. So I'm adding K plus, but K plus is not part of the reaction, so we're going to add iodine. So in this beaker, iodine ions are being added. Okay, if I blow it up and I have my iodine ions, okay, well, what do I have there? Well, I have silver ions. The question is, will silver and iodine attract each other so much and cause a precipitate? Well, that would be true if they're insoluble. So I go to my reference table. Let's go there. Okay, so table FUFU is our solubility. We see iodine are soluble, which means they normally will never make a precipitate. However, there are some exceptions. Now, I showed you an exception, didn't I? I showed you lead plus 2 with iodine. That's that yellow precipitate. But look who's also an exception. That means iodine is always going to be free ions, but if there are these 3 ions around, this iodine is going to attract these 3 ions more than it would with water and make a precipitate. So because silver plus is an exception, when it finds an ion, it's going to make an insoluble salt a precipitate. That's the key. You needed to see that there. Okay? And of course, I gave you the example of iodine with lead, so that's something you've seen before. Besides, you had this table. Okay? So the silver ion is going to hook up with the iodine and make silver iodide. Solid. It's going to make a solid. Okay? Which means what? The iodine that's added is going to take out all of the free silver. Okay, it's going to take it out just by hitting it and locking it up into a crystal. So by adding the iodine and using my solubility rules, I know something. I know that the silver, okay, ion concentration is going to decrease because the iodine will make a precipitate with Ag+. Now, we got to use Le Chatelier's principle. Nice, easy way is use my box. I've got my stress and the response. The stress is that we're going to lower silver ion concentrations, and the response by the reaction to regain equilibrium or move toward a more spontaneous process is to increase the silver ion. So what happens is that we are in need of increasing the silver plus. So we precipitate out the Ag+, we lower its concentration. That's a stress on the equilibrium. And so we look at the overall reaction here. I'm going to clean some stuff up. Let's look at the overall reaction. Okay, that's where we have to work from. Okay, and so from the overall reaction, I'm going to we're going to need to shift and respond in a way so that we're going to increase the silver ion concentration. So this reaction is going to shift in the reverse and make the reverse have some ability to have a pathway, and that's going to limit the forward. And so therefore the voltage is going to drop. Okay, so the reaction is going to shift left, okay, to increase the silver plus ion concentration, and the E0 of cell will have a decrease in volts as the forward reaction is now less spontaneous. Now, of course, you know I can't just leave that alone. What does that really mean with the U diagram? Okay, well, we have what? We have reactants and we have products. And this is equilibrium. The battery wasn't dead, so let's pretend we were like, I don't know, right here. And it's moving, everything moves toward what? Equilibrium right here. Okay, we'll call it equilibrium. It's K, Q. All right. Now, if I decrease one of the reactants, that means I'm essentially, if I'm decreasing the reactants, this dot's going to move toward the products. Remember, this is 100% reactants, 100% products. So if you've got less reactants, you're going to be in this position. So this would now drop here. Remember, this has a big arrow going forward. This arrow is now decreased, not as spontaneous. The voltage drops. So what you needed to say was that the iodine caused the precipitate, which decreased the silver ion concentration. The reaction, okay, increased the spontaneity in the reverse to increase it, which limited the forward reaction spontaneity, something along those lines. But the voltage, the forward pathway has been decreased because of increasing the reversibility of this reaction due to Le Chatelier's principle. Okay, I hope that helped.